Carbon. As you know, carbon is the backbone of all biological and organic molecules. It fits that purpose well because it can make 4 bonds. So it can, that's the most that an element can make, by the way, is 4. And so it can make a large variety of different kinds of molecules and chemical structures to make all the hundreds of thousands of different kinds of molecules that life depends upon. And another property of carbon is that it can form bonds that can store energy. And that's primarily what happens with photosynthesis and respiration. And that is the main way in which carbon is exchanged. Where am I? CO2 and H2O. Oh. Carbon is exchanged back and forth through the
that was me.
through the biosphere. No. So that's the main way carbon is exchanged back and forth through the biosphere. Okay. So these, we've got the sinks here, but these are, and I'm only going to put them on this one because these are the same sinks that we're going to talk about throughout each one of these types of elements. And I listed on the title page. These are the spheres, of course, of the Earth. The 3 physical ones: lithosphere, hydrosphere, atmosphere, and the biosphere as well. So the biosphere is a much bigger part. We've talked about these other 3 quite a bit. The biosphere, of course, is a much bigger part of what we're talking about in ecology. In this case, it does play a big part of carbon, and of course the biosphere, all things that are made from carbon, so that's crucial there as well. So we see that, of course, biological molecules are put together. They're put together by plants who carry out photosynthesis. So they actually, this equation right here represents both, by the way. That's why I've got the back and forth symbols here. So when it's going, which way is it going for photosynthesis? Left or right? Going this way or this way?
Would be going left.
That is correct. Everybody clear on that? Left. The photosynthesis part of this equation is going this way. We'll go ahead and use green to represent that. And then the respiration part of it, needs blue for that, is going from the left to the right. So you can see there, since these 2 processes are exactly alike chemically, they're just going in the opposite direction, that you can have a cycle going back and forth through there. Okay? So that's the main way in which carbon goes back and forth through in the biosphere between organisms. Yeah.
What does P stand for you?
P is for photosynthesis. Okay. So let me go ahead and put that up. Green, of course, because chlorophyll, which makes plants green, is a big part of this process. So there we go. So that's biological processes that take carbon back and forth, and this is how they cycle between them. All right. Now, human impact. So that's a major issue here. That's what this course is all about, of course. And the main ways in which we affect this carbon cycle are things that we've talked about already. And that is through burning fossil fuels and then deforestation, because deforestation affects what? Well, why write the arrow to it? What does it affect up here we just talked about? Less trees means less what process? Photosynthesis, right, photosynthesis. So photosynthesis takes CO2 out of the atmosphere, and particularly with trees, it takes it out for a long time, and respiration puts CO2 back into the atmosphere. Okay, so whatever encourages or discourages either one of those processes, either photosynthesis or respiration, there's a number of things that we as humans do that do those things. They're going to have an effect on the CO2 amounts in the atmosphere, depending upon which one of them affects. So deforestation is going to decrease photosynthesis, and a decrease in photosynthesis means less CO2 going into the atmosphere. And then, of course, that wood that's cut down is going to be either burned, which means that CO2 through combustion will go right back into the atmosphere, just like when you burn fossil fuels. Or if the trees sit there and rot, it'll go through decomposition. And that also, that decomposition most of the time uses respiration to break down stuff, so the CO2 will also go right back out in the atmosphere. Okay? So we've talked about this quite a bit. I don't want to spend much more time on this. We talked about global climate change and stuff, and of course one of the things that we're mainly concerned with is CO2 in the atmosphere is the fact that it might be increasing the Earth's temperature. But I want to focus more on something else that extra CO2 that we're putting into the atmosphere may have an effect on. And that's based on the fact that carbon dioxide is water soluble. And if you've ever drunk a soda, which is short for sodium bicarbonate, that is you've experienced this. That's what the bubbles are, CO2. Carbonated beverages are carbon dioxide dissolved in water. And so it does that. It's much more soluble, for example, than oxygen. It can hold, quite a bit of CO2. The solubility of it does decrease as temperature increases. And we talked about this also when we were talking about global climate. The fact that if the climate of the Earth, the temperature of the Earth rises, that the CO2 in the ocean will become less soluble, and so more CO2 will come out, and therefore it could get warmer again, which would make the oceans warmer again still, more and more and more. What kind of process do we call that? What kind of feedback? Positive or negative? Positive. Positive feedback means it gets the effect increases more and more. Okay. So when CO2 dissolves in water, it goes through a little reaction, partial reaction to be completely honest with you there, but it forms hydrogen carbonate. This is also known as carbonic acid, which, by the way, this is why they put it into sodas, because acids are sour, and therefore this makes it acidified a little bit. It gives it that extra tanginess kind of flavor to it. But this isn't soda science, so we'll move on from that. But that's the basic reaction with CO2. This is how it dissolves into the water. So as an acid, I don't want to get into the details of acid-base chemistry, but the H's are going to come off, and then this CO3 ion is going to be dissolved in the water as what we call a carbonate ion. Okay. This is good because those carbonate ions, let's go ahead and write that in there in case you forgot your chemistry. Okay, carbonate ion. And this is good for a lot of the creatures that are in the ocean that have shells, because they absorb that carbonate ion and combine it with calcium to make calcium carbonate. Okay, we know this. We've got the piece of the Florida lithosphere that is calcium carbonate. Limestone's another word for it. There are large deposits of this in many places around the world. This is why we have our aquifer like we do. This is a crucial reaction that goes on in in the ocean. So it's good that it has some of that in there. But the problem is that this also, of course, since this is an acid, overall extra CO2 dissolving into the ocean lowers the pH, makes it more acidic. We all know that lower pH means it's more acidic, and this will actually interfere with the calcification process because acids dissolve calcium carbonate. So there's it's a very fine, like many things in nature, it's a very fine balance between having enough carbonate ions in there for the marine organisms to be able to absorb them and build their shells, but to the point where it hasn't affected the pH that much, to the point where you have so much that even though you've got plenty of carbonate ions now, it actually makes it harder for them to carry out this calcification process. Now this is true not only with exoskeletons with calcification, but calcification technically also is how skeletons harden. And although we haven't really seen in the ocean that being an issue with the fish and weaker skeletons, it is been shown in lakes that have a low pH because of acid rain, which of course is a stronger acid than your carbonic acid, but because of the acid rain of the nitric and sulfuric acid, you see fish in those areas. One of the effects you see is the fish have weaker skeletons, and the waterfowl, ducks, and also turtles. They're of course not waterfowl, but turtles and other reptiles that lay their eggs in the water. A lot of times their eggshells in those kind of acidified lakes are not as strong. Now, same reason, because of low pH, not exactly the same source. This is from CO2. The acidified lakes are more from acid rain, which as we know is different. But same thing, same chemical idea that acids dissolve minerals like calcium carbonate. Any questions about carbon cycles? So we've got the basic back and forth of respiration and photosynthesis. You've got the human impact, which primarily of burning fossil fuels, putting carbon dioxide in the atmosphere, cutting down lots of trees. That also increases the CO2 in the atmosphere. And then you've got the issue of carbon dioxide dissolving in the water, and what that does, how that's affected by the temperature, and the fact that can acidify the oceans, and that can be harmful to organisms that make shells and stuff like that, as well as other things. There's other things I didn't go into, but it's lower pH effects. So that's kind of the many different things that are affected by that. All right. Nitrogen. Okay. Now, we talked about carbon. Listen up, please. And when you look at your three main biological molecules, and when you think about what these are, you can just think about what they always talk about in diets. That's a very common subject, of course. Everybody's concerned with their diet, etc. But what are the three things they talk about? What are the three main types of food they talk about? Proteins, carbohydrates, and fats. Carbohydrates are sugars. Fats. Proteins, carbohydrates, and fats. So carbohydrates and proteins are mostly carbon, hydrogen, and oxygen. Okay. Proteins are also mostly carbon, hydrogen, and oxygen, but they also have a large amount of nitrogen. So that's the main role that nitrogen plays in biological systems, but it is also a primary component to nucleic acids like RNA and DNA. So it is kind of the third most common thing you'll find in living systems. And but most of the nitrogen that exists on Earth is actually in the atmosphere. Anybody remember how much or what percentage of the atmosphere is nitrogen?
74%.
A little bit more.
80.
About 80, yeah, 79 to 80 in that area. Okay, So 79 to 80% of the Earth's atmosphere is nitrogen. It is nitrogen gas, so I'll go ahead and take that answer. But what is the formula? What's the formula that nitrogen gas takes? N2, right? It's a diatomic molecule. It's one of the Brinkelhoffs. You guys remember that from chemistry? Or if you want to talk about Brinkelhoff, you remember Brinkelhoff? Nobody learned that? Nobody. Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Maybe leaving some out there. I think that was it. Anyway. So, all right, enough reminiscing about chemistry. So nitrogen is one of those, and it is a diatomic gas. It's a very stable substance. We talked about that when we talked about the atmosphere. How it's kind of like a nice neutral thing to help stabilize the atmosphere. But because of that, it's not available to I would say most living organisms, because life is about chemical reactions, and things that don't chemically react very well. You have to have certain special enzymes and stuff to make them do that. Fortunately, we have bacteria that can do that kind of thing. And they fix it. Not that it was broken, but when you fix things, and we're talking about nutrient cycles and what they call biogeochemistry. I think I put that word on here somewhere. Did I put that on here? Well, anyway. How we do those different things. Fixing is when you take an element that is normally out in the environment or is out in the environment and put it into living systems. So photosynthesis in trees, for example, and other plants, and through the process of photosynthesis, fix carbon. There are bacteria who, through a number of different processes, we're not going to go into the details because it's mind-boggling, but they fix nitrogen. They take the nitrogen gas out of the atmosphere and they put it into themselves, and then they end up making it into a form that the plants can use. Okay, so this is the big part of the nitrogen cycle there. And the second major part of the nitrogen cycle is through decomposition. So this is where we first start seeing the decomposition process have a big impact on making nutrients available to producers and therefore the rest of the food chain. So, like I said, the first step is getting it out of the atmosphere itself, and we call that nitrogen fixation. It starts with nitrogen gas into, and through a number of different reactions, bacteria will convert it into both ammonia and nitrogen dioxide, nitrogen and nitrites and nitrates. Excuse me. Sorry about that. Nitrites and nitrates. That's why I got the X there. NO2 and NO3, but in this case they're not the gases NO2 and NO3, they're the ions NO2 and NO3. So it's very confusing, I know. But this is a NOx, but in this case it's not a NOx gas, it's a NOx that's dissolved in water. Let's do this. Let's put a little negative sign up here. So that'll help you hopefully remember that it's an ion, not a gas. Okay? Both NO2 and NO3 are -1, by the way. Okay, so that's done mainly by bacteria, but there's a pretty fair amount of this actually that also happens with lightning. In the case of lightning has a high enough temperature and everything that it can react the nitrogen and the oxygen that's in the air right around it. Just like we see happens inside automobile engines and high temperature furnaces. And then produce one of your gaseous nitrogen oxides, which then reacts with rainwater, producing both your nitric acid as acid rain, but also means that it will rain down nitrates from when you have electrical storms. Okay, but by far the biggest component, the biggest part of it is your bacteria that do this. Okay. Now the next one, assimilation. This is what plants do in general. So this is a general term. In this case, we're talking about it for nitrogen, but it's also what plants do when they make, for example, the glucose from photosynthesis into cellulose. It's when plants build biological molecules. That's what assimilation is. And when I say biological molecules, the main ones, once again, fats, proteins, carbohydrates. Okay, those are your biological molecules. I've talked a bit about this, about how they're different than the individual, than the carbon dioxide or the nitrates and nitrites, and what we'll see sulfur and phosphorus. And that's a connection. Those have to be broken down for the plants to get it back. Okay. So the plants put all this together, they make biological molecules. That's carried out by plants, or more accurately, primary producers, because we're also talking about algae as well. But these, so that's what they do, and they of course get eaten. Okay, they get eaten, and now we've already talked about the carbon cycle. So that part they got eaten, and then we exhale out the carbon dioxide. Now we're going to talk about urine. So don't get pissed. All right. We excrete the nitrogen after we break down our foods and stuff, primarily in your urine. Okay, as well as other organisms, and they excrete, if they're simpler organisms, they just excrete it directly out. But the point is that nitrates are water soluble, so when water is carried out, carries waste products out. This is a big part of the waste. And then bacteria will take that, the nitrogen containing compounds in there. The main one is urea, as you might imagine, but the bacteria will convert it into ammonia. Or ammonium, actually, we'll say. Okay? And then, so that's there. Now, plants can use that a little bit, but most plants, the easiest nitrogen form for plants to utilize is your nitrites or nitrates, your NOx's. And once again, let's put this.
What?
NOx, which can be nitrites or nitrates, which is nitrites or NO2, and nitrates or NO3. So I just okay. So these are dissolved nitrogen-containing compounds. They're in the soil. It's what we use when we use fertilizer. As a matter of fact, the most common fertilizer is ammonium nitrate. So you get both forms of it when you put that down. It's also very explosive, but and that dissolves in the ground, and plants can take that up readily. And that's by far the biggest input of that nitrogen is from what we do by making those fertilizers. Okay, but in nature, bacteria will do this. They'll convert ammonia into nitrites or nitrates. That's called nitrification. Okay. Now, I didn't name these, so I don't know why denitrification is not. Okay. Chemically speaking, is not the opposite of nitrification, but it's not. Another thing to add something else to the whole picture that happens is in the soil there are bacteria. Put that in there, I don't have that. That convert nitrates and nitrites back into nitrogen gas and N2O. So it's really the nitrogen fixation that is the opposite of. So up to me, I would have called this nitrogen breaking, but I guess they don't like my ideas. But it's the opposite of fixing it. They're taking it out of living systems, basically putting it back into the atmosphere. Okay. So the nitrogen, when that happens, is not a big deal, but this, I would be happy if you remembered that is a greenhouse gas, so either group 2, either you remember that, or, oh yeah, by the way, there should be a subscript there. Or you're just guessing at it, but that's good. There was 4 main greenhouse gases we talked about: CO2, methane, N2O, and CFCs. Okay.
What's the last one?
CFCs. I review a lot, like, when I'm kind of just conversing, so to remind things. So, that was CFCs were back when we talked about global climate change. So anyway, there's our N2O. So that's part of the whole global climate change. I think I discussed this. I briefly referenced that we increase N2O through using fertilizers, which is what we do. When we put down these nitrogen-rich fertilizers in the soil for agriculture, we increase the amount of this denitrification that goes on, and therefore add more N2O to the atmosphere, and N2O is a greenhouse gas. And so we know the problems with that. Thanks. People are introducing nitrate and ammonium fertilizers. Usually it's just both of them together. Like I said, the most common fertilizer is ammonium nitrate. But we put a lot of other stuff on the soil as well. But, and we also, if you may remember, from air pollution, we produce nitrogen oxide gases, both through automobile combustion and the kind of high temperature furnace combustion you'll get in fossil fuel plants and steel mills and stuff like that. So under very high temperatures, you can make the nitrogen and the oxygen, or pressures like in an automobile engine, react the nitrogen and the oxygen together, produce your nitrogen oxide gases, your NOx. Okay. It causes pollution. You know what, group 4? I'm sorry, it's too big. Too late in the year to be taking extremely general answers. What specifically? What type group of pollution that causes a particular process to happen because it fertilizes the lakes? Eutrophication is what I was looking for there. And as I just mentioned, in the soil, the bacteria, the denitrifying bacteria in the soil eat that, consume that fertilizer also, and they give off the N2O, which is a greenhouse gas. Oh, look at that, I repeated myself. Oops, well, just said that. Burning fossil fuels gives us NOx. All right, and then, yeah, so also, NOx is NOx in the atmosphere, as we've talked about before. This creates an acid rain, nitric acid in the atmosphere. And it is part of it combines with your gasoline fumes. And this is what makes the photochemical smog we talked about with air pollution. That produces what, for example? Or anybody else remember a component of
photochemical smog?
Kyle.
I know, I was just repeating it.
Rise and shine. Anybody remember? We love it up there. We hate it down here.
Ozone.
Photochemical smog. Yes. Could you repeat the question? Ozone's one of them, and a bunch of other stuff and everything. But that is a common problem. Any questions about nitrogen cycle? All right.
Pro-choice.
Okay, so phosphorus. What do we need phosphorus for? Well, it is a major part of your nucleic acids, which would be RNA, DNA, ATP as well. Hopefully those acronyms ring a bell for you. They're not really acronyms unless you're saying it like a word, right? So you know what I mean. Those initials make sense to you. If you remember the double helix structure of DNA, the parts between the things that connected each one of those steps on the sides, the sides of the ladder, so to speak, those are phosphate bonds that are in there. And of course, ATP is adenosine triphosphate and diphosphate, so those are some of the roles they play. They're also a big part of our bones and the shells of marine organisms. Okay. We do mine it. Most of phosphorus is in the lithosphere. One reason for that is that it doesn't have a gaseous component for the most part. Under normal conditions, gaseous. Phosphorus does not form gases under normal conditions. It's also very insoluble. So we do mine for it. As a matter of fact, any ideas on what one of the biggest, if not, actually I believe it's the biggest phosphate mining state in the United States is? Any ideas?
Oklahoma.
Montana, Oklahoma. I'll give you a hint. It's closer than that.
Alabama.
Alabama, Georgia, getting closer, even closer than Georgia. How about Florida?
How about Florida?
How about Florida? So a lot of people don't think of Florida as a mining state, and we don't really mine for metals so much, but we do a lot of phosphate mining. A lot of, like I said, it's in the shells of organisms, and of course we know that most of our substrate is old coral reefs and limestone and stuff like that. So there's a lot of that in there. Okay. So we do mine for it, therefore, of course, we're getting it out in the environment, and also we put it in our fertilizers. That also gets it out in the environment. No gaseous components, and phosphorus compounds are usually not soluble in water. The exception, though, is, I will say, and hopefully you remember this, way back when we did water pollution, was the substance called superphosphate. Anybody remember that?
Yeah.
Yeah, superphosphate. What's up? So superphosphate is a man-made chemical type of phosphate that does actually dissolve in water. Not super well, actually, but it dissolves much better than most phosphates. And that's why it's become more of a problem as far as water pollution goes. And it's used in fertilizers and detergents, but not as much in detergents anymore. We phased a lot of that out because of that particular problem. Yeah, so it's constantly often a, no, not small factor, limiting factor. Now this limiting factor business is kind of a tough thing. So oftentimes the limiting factor, because of its insolubility, so a lot of times it just sinks down and becomes part of the ground again. It doesn't get transported around through the atmosphere. So oftentimes it's in short supply, relatively speaking. There's there's a good bit of it in normal soil, but organisms need a lot of it. It's kind of hard for them to get in because of its limited solubility and the fact that it's not going to be transported through the atmosphere. So when we talk about it being a limiting factor, that just means that usually in both, at least in terrestrial ecosystems, it will be the thing that will run out the quickest for plants. And in aquatic ecosystems, it is often the thing that keeps a lot of your algae and stuff, the lack of it, because it doesn't dissolve very well, it keeps your algae populations to a minimum. Okay, which, as we know, is a good thing for the rest of the lake. And once again, this is when we make substances, phosphorus substances that are more soluble, they get in the water, then the algae goes crazy because, like, well, we've always had plenty of nitrogen and all the other stuff, but now we've got phosphorus. Boom! Let's have a party and make lots of babies. So that's baby algae. So that is the role and the conundrum, if you will, of phosphorus and its role in the environment and how the solubility affects all of that. Okay, like I said, phosphorus a lot of times, once it's been used by an organism, it ends up back in the ground. One of the reasons why is that, well, what does guano mean? Anybody know what guano means? Guano. Guano. Bat what? What? Come on. Bat poop, right. Give me enough hints there. Bat poop, yes, guano. And it's just one example. There just happens to be, because bats a lot of times are in caves, a lot of it does not, that poop does not escape. But the same is true on land or out in the open and in the ocean, is that a lot of that phosphorus, once it's excreted as usually as feces, it's going to settle down and then just go right back down in the ground and become part of the lithosphere again. It doesn't keep cycling as much through the environment like nitrogen does. And so, of course, carbon as well. So one way to remember this, I always tell you, you pee nitrogen, you poop phosphate. P for poop, P for phosphate, however you want to do that, but that helps you to remember that. But a lot of the lithosphere, a lot of the components we have there come from living organisms, and specifically the poop of living organisms. And also, of course, the dead organisms as well. So that's what a lot of the phosphorus in the ground is from. Over time, of course. All right, questions about phosphorus? Its roles, plays, and why it's, you know, its chemical properties, and the fact that it doesn't move around a lot. Kind of a boring chemical in that respect, but very necessary for living organisms. That makes it limit ecosystems and things like that. All right, sulfur. Now, sulfur is a major, not a major, but it's, yeah, there's a lot of it in proteins. It's not one of your primary parts like carbon and hydrogen and nitrogen is. Sulfur. There we go again. All right. When are you guys going to check your slides? Huh? Those slides are still sitting over. You haven't checked them yet. Those of you who were here Thursday will understand that reference. Okay, protein. Protein. And this is why carnivores poop stinks more than herbivores. So have you ever been like cow patties and stuff? I mean, it smells bad in large quantities, but it's not really disgusting like if you have the same amount of human poop or tiger poop or something else like that smell is sulfur. And that's why also if you eat things that have high sulfur content, you're gonna gas up the place. It smells bad. You'll have more gas, it'll just be stinkier. It's a very common component of the lithosphere. Most of the sulfur on Earth, just like most of the rest of these, except for nitrogen, the biggest sink for it is the lithosphere. So when we mine for stuff, and when we burn stuff that we mine, mostly coal, then we're going to be releasing that sulfur into the atmosphere, or in the case of mining, we will expose it. And there's actually a lot of bacteria that like to eat sulfur. So, as a matter of fact, since we're discussing all things gross, the odor of flatulence while your farts stink is because of these bacteria, these types of bacteria in your body, in your gut, that like to eat the sulfur that's in your food and produce hydrogen sulfide. It's actually the hydrogen sulfide itself, H2S, that's the really stinky. That is the common rotten egg, sewage type smell that you get. That is, of course, what makes your flatulence stink. And that's also why some people have much stinkier farts, for lack of a better term, than others. So anyway, that their diet, of course. So yeah. Aren't you glad you came today to learn about all this stuff? Yep. Why they stink. So maybe you remember when we talked about mining. This leads to this same consumption of sulfur by bacteria. A lot of times they will turn it into sulfuric acid, and that creates acid mine drainage. So that's another part of the environmental impact we get from digging stuff up and exposing sulfur. And we do mine for sulfur as well. Sulfur is used in a lot of compounds. As a matter of fact, the most commonly produced industrial chemical is sulfuric acid. So there is a lot of that in there, a lot of it around and available in the different things that we do. All right, questions about sulfur? No? All right, so finally, micronutrients. Iron, magnesium, zinc are essential nutrients, and this is the one you needed to put small for. Who put small before for limiting? What group was that? Okay. Yeah. That's where you're supposed. That's where you should put it. Yeah. Micro means you don't need much, so it's necessary in small amounts. The Did I give examples? Yeah, iron, magnesium, zinc, copper. And you look at the back of a vitamin bottle and all the things they list there, those are many of your micronutrients. And so they're things that we need, just not as much as the big four, excuse me. They may also be limiting factors. And you may remember that I talked about orange trees. You remember what citrus fruit, what particular mineral they need? It might not be in the soil that much. Manganese. Anyway, not that important, but manganese is, just it happens to be necessary for certain types of enzymes and stuff, particularly in citrus fruit, and it's easily was depleted when they tried to grow citrus in other parts where there wasn't as much manganese. Citrus is native to the Amazons and the mountains there, the Andes Mountain. So the practice of monoculture, that was one of the things we talked about when we talked about bad or soil depleting agricultural processes. Planting the same thing year after year, you have a good chance of depleting all of a particular micronutrient mineral out of the soil for that. That could harm that crop. Any questions? All righty.